So what we're going to do now is I'm going to go ahead and start taking a look at some source code. One of the things that we really want to do in this course is look at code. I made the point early on that it's not enough just to talk about concepts. It's not enough to just talk about the theories or the features in the abstract, but we really want to look at some code. And the code we're going to look at here is an example that shows up in the various videos, and I analyzed the pieces kind of in isolation in the various videos. But I don't think there's any video that really talks about the program that we're going to look at as a whole and analyzes the overall structure of the application, looking at some of the interesting helper methods and so on and so forth. So that's what we're going to do today. And this particular example is something that's called the SearchStreamGang program. And you'll see a bunch of examples of SearchStreamGang throughout the other videos in the course. So what I'm going to do now is I'm going to go ahead and share my screen, and I'll first show you where you can get this code just as a reminder, and then we'll take a look at the code itself. So if you go to my live lessons GitHub repository, which has lots of examples that I use in various ways, and you poke around here and go to SearchStreamGang, you will find the code that we're going to be looking at here. And this particular project basically demonstrates a whole bunch of different Java features, modern Java features, classical Java features. So we've got lots of functional programming stuff like lambda expressions, method references, functional interfaces, and then a bunch of modern Java concurrency and parallelism mechanisms like parallel streams and completable futures and so on, and the Java fork join framework, which is a bit more object-oriented. And we're also going to take a look at some object-oriented examples just to kind of provide a baseline for all the other cooler functional stuff. And we're also going to take a look at some very modern approaches based on the reactive streams API, which will essentially be RxJava and Project Reactor. And so some of this stuff is brand spanking new because I added the features over the weekend just for fun. And so we'll walk through this a bit at a time. So the point of tonight's discussion is going to be to give you the big picture view of the overall application. And we'll probably take a look at one or two of the different implementation strategies, but we'll look at the more advanced ones as we get further in the course and have had a chance to talk about parallel streams or completable futures or RxJava and Project Reactor and fork join pool and so on. So with that, we'll now go ahead and switch over to my IDE. And if you clone the repository, this is what you're going to see because I updated it very recently. So what this basically does is it's kind of a fun way to compare apples to apples in terms of these different implementation strategies for an embarrassingly parallel program. And what this embarrassingly parallel program does is it takes the complete works of Shakespeare. There's basically 38 works of Shakespeare if you count all of his sonnets as a work. These include, of course, all of his classic tragedies like Hamlet or Julius Caesar, as well as his various comedies, such as Midsummer Night's Dream and As You Like It and so on. And each of those things comes in as a separate file. And then we also have another file which contains various famous quotes from the bard, like neither a borrower nor a lender be, or to thine own self be true, et cetera, et cetera. And what we're going to do is we're going to go ahead and apply all kinds of different mechanisms to search all these files containing the works of Shakespeare, looking to see where the various works, where the various famous bard quotes appear in those works of Shakespeare. And there's a couple different ways to run the program. One way to run it is in so-called verbose mode, where it will actually print out where all the things were found. And another way to run it is to run it in performance test mode, where you can compare and contrast the runtime of the different implementation strategies. And as you can see here, there's a bunch of implementation strategies. There's over a dozen of them at this point. We have some that search for the famous bard phrases in the files using completable futures, a couple different variants there, the fork join pool, a whole bunch of different variants of Java parallel streams, the Project Reactor, reactive streams framework, the RxJava reactive streams framework, and then a couple of other examples we have as kind of baselines, one of which is a sequential loops implementation, which is kind of our bare bones, old school way of doing the code. And then we have a sequential stream implementation, which is really there to demonstrate the overhead of sequential streams qua streams, and then to provide the basis for being able to do the parallel implementations of streams. And so that'll give us a chance to really do a nice apples to apples comparison in terms of runtime. Speaking of runtime, let me go ahead and run the program. And I think it's kind of fun to see how it behaves. So you can see what it does is it starts up and it starts going through all the various strategies, running them all. And we'll take a look and see how this works. And it ends up giving 42 phrases that match within the 38 files that are the works of Shakespeare. And when we're all done, it prints out the results of our 15 or so different implementation strategies, and it sorts them from fastest to slowest. Now, in my particular platform I'm running now, it's an 8-core MacBook Pro with 64 gigabytes of memory. So it's a pretty beefy machine. I'm sure you guys have access to even faster machines. It'd be kind of fun to see how they perform. But you can really see the benefits of parallel computing, especially when applied to this embarrassingly parallel style of program. So just to see how it works, you can see that the sequential streams version took about 3,600 milliseconds to do all the processing. In contrast, the sequential loops version took about half that amount of time. So that's kind of quantifying at a coarse grain level the overhead of just using streams. Well, you might think, well, why the heck would we ever use streams if it's going to add all this additional overhead? Well, the reason is because it's absolutely trivial to take the sequential version of all this stuff and parallelize it. And with just a couple of minuscule little tweaks, we can go from the slowest running strategy in the list to the fastest running strategy in the list. So search with parallel streams is just the sequential version with stream replaced with parallel stream. That's the only change. And you can see that the performance boost is basically about linear. So there's 8 cores, and so what took 3,600 milliseconds with one core sequentially takes about 485 milliseconds when we run it with the parallel streams version. So the point of this is that with almost no change to the code, we can get massive, essentially linear speed up in performance on a multi-core processor. And that's pretty darn cool. And then you'll also see that all the other implementations are very much in the hunt. So there's not really that much appreciable difference between the fastest of these and even the slowest of the different concurrency and parallelism models. They're all way fast. But I think it's kind of fun that the version that performs the fastest is the one that does a trivial little tweak to the sequential streams version. So that's really the beauty of streams. You can scale them up quite nicely with minimal effort. And we'll come back and talk about that both in the examples we look at here throughout the course, and of course, if you watch the other videos for the course, you'll also learn more about how and why that works. So the way the program works, this is, of course, the driver program. We define a map called a strategy map, and it maps the appropriate tests to run, which is this enum, to something called a SearchStreamGang. And a SearchStreamGang is basically a superclass, an abstract superclass that's used as the basis for each of the different implementations we're going to look at, the so-called implementation strategies. And I make this a linked hash map. And the reason I make it a linked hash map is that will preserve the ordering in which I gave these tests to run. So when I iterate over the map, it'll give the results in the same order that I put them in the enum. If I just used a regular old hash map, then the iterator would just be whatever order they happen to hash into that hash map. But if I use a linked hash map, then it keeps the iteration order in a way that can be done in a fixed order, which I want to do. Hashing is still done using a hash function, but iteration is done in this linked manner. Then down here we have a single text file that contains the complete works of Shakespeare. We'll take a look at that in just a little bit. And then we also have something that's the list of phrases. So let's go ahead and take a look real quick at these. So here's the complete work of Shakespeare. And I won't belabor you to go look at all this stuff, but it's a pretty darn big file. It has about 5.5 megabytes into 5.5 megabytes worth of Shakespeare text. And then over here we have a list of famous phrases by the bard. like to be or not to be, that is the question, or the lady doth protest too much, methinks, or beware the Ides of March, all these great classic quotes from Shakespeare. And that's what we're actually going to use to look up in the program in the works of Shakespeare and see if we can get the matches to find them. Okay, here then is the main program. We parse command line arguments. For example, if you give it the -v flag, it'll print out the results, mapping the phrases to the various plays or works in which they match. We then go ahead and we create a list of care sequences, and we do it this way so that we could actually have the complete works of Shakespeare, followed by the complete works of J.K. Rowling's, followed by the complete works of, I don't know, J.R.R. Tolkien, whatever. You could have different input sequences or corpi that you could search. And this is a pretty clever little approach. I'll walk through this because it's kind of fun. We're going to go ahead and take the Shakespeare data file, and we're going to go ahead and split it up into chunks, one chunk per work. And the way we do that is if you were to go back and look carefully at the work of Shakespeare here, you'd find out that there's an @ sign that's used to separate each of the works of Shakespeare. So if you look for @ sign, you can see that each of the works in this file is begun by an @ sign, since there was no @ sign in other parts of Shakespeare. And so armed with that knowledge, we then go ahead and have this method here called get shared input. And what get shared input does is it takes a file name, namely the complete works of Shakespeare file, and a splitter character, which is the @ sign, and it goes ahead and it opens up the file in our system resources folder, and then it reads all the bytes of the file into one character sequence. So now we've got a big honking character sequence with, 5.5 megabytes worth of Shakespeare text. And now we're going to go ahead and do some really cool streams manipulation. So we start out by basically doing this pattern compile. So if you're familiar with Java regular expressions, we have this concept called a pattern. And in this particular case, we're going to go ahead and compile the pattern using the splitter. So we're creating ourselves a regular expression that's going to be the @ sign to split up the input character sequence into strings. And then we use the split as stream method to take the complete works of Shakespeare and create a stream of strings from that. So this is just good old streams pipelining at work. So we create ourselves a stream. This is a sequential stream. And then we go ahead and we get rid of any empty strings. If there happen to be empty strings, we just ignore them. And then we go ahead and map each string into something called a shared string. And shared string is a clever little class that I wrote to work around what I think is kind of a glitch with Java. Other people would argue it was an enhancement. But starting with Java 7, they decided that they were going to change the semantics of substring to make a deep copy whenever you do a substring. Whereas before that point, they shared the actual contents, and they just made like a new sort of header to plop on the beginning of the substring. So I didn't like that for my purposes because it made too many extra copies. So I created something called a shared string that is based on a character sequence. And the reason for that is that character sequences have a different semantic for subsequence. So for subsequence in a care sequence, you can actually end up sharing things in a much cleaner way. And so this is just a way to kind of optimize the program when it comes to copying. So we now end up with a stream of shared strings. And the last thing we do here is we use a good old terminal operation called collect, which triggers all the intermediate operations here, including the compiling to the splitter and splitting as the stream and blah, blah, blah. And then we collect the results into a list. So this particular method returns a list of character sequences, where each character sequence is a different work of Shakespeare. So that's how we end up getting the works of Shakespeare into an array list. And then down here, we do the same thing with our file containing the phrase list. And this is pretty much the same idea. We open up the file, we get rid of any empty strings that might happen to be in there, and then we create ourselves a list of strings, which is the strings to search for in the list of character sequences, which are the works of Shakespeare. And if you think about this from a parallel programming point of view, you can imagine that searching for all these phrases in all the strings can proceed quite nicely in parallel with no dependencies between any of the processing, leading to what's commonly known as embarrassingly parallel processing. And whenever you have a chance to write embarrassingly parallel programs, you should take it because they tend to scale up pretty much linearly as long as you use the right features in Java and as long as you have a good implementation of your Java execution environment. So at that point, we're going to go ahead and do some other fun stuff. We're going to make a call to a helper method called make strategy map. And we pass in the phrase list and we pass in the input data. And notice these things are all passed by reference. So we're not making extra copies of this stuff. We've got one big copy of 5.5 megabytes worth of the work of Shakespeare, but then references to those things are passed around. So we don't actually have to make copies of them. Let's go take a look at make strategy map. This is a very clever method too. What it does is it iterates through all of the tests to run. Remember, that's the enum that we defined way up here. These are the tests to run. And for each of the tests to run, what we're going to do is we're going to switch on that test. We're going to switch on that enumerated value. And depending on what the value is, we're going to go ahead and add an entry into the strategy map. So for example, if it's the fork join enum, we make ourselves a new instance of search with fork join, which is the implementation strategy that implements the SearchStreamGang superclass, and we'll use the fork join algorithm to do the searching. And we do similar things for sequential loops and sequential streams and parallel streams and completable futures and Project Reactor and RxJava, blah, blah, blah. So what we're doing is we're basically building a little map that maps the type of the test to the implementation strategy that implements that particular test. And then we're going to use that henceforth when we actually run the tests. So actually, after we've populated that map, we then go ahead and call the run tests method. And this is pretty much where all the magic actually happens. So let's go take a quick look at run tests. So run test takes the phrase list and the input data. And I guess looking at this more carefully, we don't actually have to give it the phrase list and the input data anymore. That was left over from an earlier implementation where I had done these things in a slightly different order. So let's go ahead and zap that. We don't need that code there. And now what we do is for each of the test search stream implementation strategies in the map. So for each is basically a Java functional interface method that was added to allow us to iterate through every element in the map. And in this case, we're going to basically get back the key value pair for every element in the map. For each of those key value pairs, we're going to go ahead and print out that we're starting to run the test. Then we're going to go ahead and call the run hook method on the implementation strategy, each of which implements the runnable interface, so they all have a run method. And that'll go ahead and run and do the computations. Then when we're done, we go ahead and call the garbage collector to basically reclaim all the memory so that the next test can start with all the resources allocated. And we keep doing that, and we print ending tests. We do that for every one of the strategies. And we'll look in this in a bit more detail in just a minute. And then when we're all done, we're going to go ahead and we're going to print the results. And that's, of course, going to print out all the things we saw here with all the different timing results that we saw. So that's basically what run test does. And I just wanted to kind of give you an overview of the test driver before we start looking at other parts of the implementation, which will get much more interesting. But this just gives you a sense. Even this simple program illustrates a whole bunch of fun Java programming techniques, like the idea of putting all the strategies into a map so we can look them up by name, so we can keep track of them in a very clean way. Demonstrates the fact that you probably want to do the garbage collection each time so that you don't end up penalizing someone who came later than someone who came first and they've run out of resources. And something else I did here, another reason why I wanted to make sure that we used a linked hash map, is I always want to make sure that the warm-up fork join thread pool enum gets run first. And the purpose of that is just to make sure that it goes and warms up the thread pool. There's something called the common fork join pool, which all these implementations use. And we want to make sure that all those threads are up and running so that when the other tests start running, where we're really going to measure their performance, we want to make sure that the thread pool is warm. And that's just a way to make sure that the timing results are a bit more consistent. So that's an overview of the SearchStreamGang test driver. We'll now go ahead and take a look at the other elements that provide the infrastructure for this program.